This is our second presentation on interconnected systems. We'll examine two aspects of system interconnections. First, we'll look at the impulse response of interconnected systems. And then, we'll examine the loading phenomenon in interconnected systems. Let's start by looking at a parallel interconnection and examining what the impulse response will be. In a parallel interconnection, the same input goes into both blocks. When we look at impulse response, we're talking about applying an impulse to the input. So, we'll have an impulse going to both H1 of S and H2 of S. In response, these two blocks will produce their individual impulse responses, H1 of T and H2 of T, which will be the inverse Laplace transform of the transfer functions. These impulse responses will then be added at the summation junction to make the impulse response of the parallel system. So, if we have two systems in parallel, the impulse response of them will be the sum of the impulse responses of the individual subsystems. That is, HP of T will be equal to H1 of T plus H2 of T. Let's do an example. H1 of S will be 1 over S, and H2 of S will be 3 over S plus 1. H1 of T then is the inverse Laplace transform of 1 over S, which is the unit step. And H2 of T is the inverse Laplace transform of 3 over S plus 1, which is 3 e to the minus t u of t. So HP of T will be the sum of these two, and will be 1 plus 3 e to the minus t times u of t. Now let's look at the impulse response of two systems in cascade or series interconnection. Delta of T is presented to the first system as an input. The first system is H1 of S, and its output will be H1 of T in response to delta of T. H1 of T will then be an input to H2 of S, and then the output will be the response of H2 of S to the input H1 of T. Now, for linear system H2 of S, we know its output will be the convolution of the impulse response of the system H2 of S and the input. Therefore, the output of the cascade, which we label HC of T, will be the convolution of H2 of T, the impulse response of H2 of S, and its input, which is H1 of T. Therefore, HC of T is H2 of T convolved with H1 of T. Now you know for convolution that the order of operation makes no difference. So we could also write HC of T is equal to H1 of T convolved with H2 of T. The convolution of subsystem impulse responses yields the interconnection impulse response. For this cascade interconnection, let us suppose that both subsystems have impulse responses that have finite width. Suppose H1 of S has an impulse response H1 of T, and it has width capital T1, and H2 of S has impulse response H2 of T, and it has width capital T2. We know the width of the convolution of H1 of T and H2 of T will be T1 plus T2. This will also be the width of the impulse response of the interconnected system. So, the width of the interconnected system's impulse response, which will denote T sub C, will be equal to T1 plus T2. This result tells us that the time it takes for a cascade system to fully respond to a step input will never be faster than that of its slowest subsystem. That is, the slowest subsystem is the bottleneck in a cascade interconnection. It will dictate how fast the system's output can respond to the input of the cascade system. Unfortunately, there are no similar results for the feedback interconnection. It's very difficult for us to assess what the impulse response of the feedback interconnection is like in terms of the impulse responses of the individual subsystems. The relationship is just not simple at all. The feedback interconnection's impulse response will be the inverse Laplace transform of the closed-loop transfer function, which is h1 of s over 1 plus h1 of s h2 of s. It's very difficult to assess even the speed of response of the feedback interconnection. It may even be faster than that of either subsystem. We now turn to the important topic of loading. Loading refers to the property of the interconnection of systems changing the dynamics of one of the systems. We've assumed in all the interconnections we've made in our block diagrams that the dynamics of the individual subsystems is not changed by the act of connecting them together. Now, a block diagram can never show the change that would occur, but these may happen, in fact, due to the physics that underlie the block diagram. The term loading comes from electrical engineers. They refer to certain circuits, say, as not loading other circuits. But loading can occur in mechanical systems as well. And when we're doing modeling, we have to be careful about the issue of loading. We must carefully consider it when we think about interconnecting blocks together. Let me introduce some examples where loading is not present, and that will give you a better idea about what we mean by loading. Let's take the example of an oven. The input to the oven might be the current that's supplied to the heating element, and the output of the oven would be its temperature. We might think about interconnecting the oven system with a thermocouple, which will measure the oven's temperature. It has the temperature as an input and produces a voltage as an output, which is read on a display. The act of measuring the temperature with a thermocouple does not affect the heating behavior of the oven. The oven responds to the current in the same manner as if the thermocouple was not present. The dynamics are unchanged. A second example of no loading is the attachment of an accelerometer to a structure, perhaps a building. The accelerometer measures the vibration and produces a voltage. The building responds perhaps to an earthquake, forces on the ground, and that causes the structure to vibrate. The act of connecting the accelerometer to the building does not change the way the building vibrates in response to the earthquake forces. So there's no loading in this case. But that does not mean that you'll never see loading with an accelerometer. The loading issue in mechanical systems is often size dependent. The building vibration to an earthquake is not affected by the presence of an accelerometer. But if we wish to measure the vibration of a fly's wing in the same manner, the motion of the wing of the fly would be affected by the addition of the mass of the accelerometer to the wing. Thus, if we wish to measure something like the vibration of a fly's wing, we have to use some other technique of measurement other than accelerometer, perhaps an interferometer. The attachment of the accelerometer would load the wing, but the use of an interferometer would not. From a block diagram point of view, this issue of loading would not be apparent. We would have an input-output relationship for the fly's wing and another one for the accelerometer, and neither of these blocks would show the dependence of the interconnection. Later in this course, we'll consider mass spring models of mechanical systems, and we'll write the equations of motion for these. So, if we were to consider the first system, shown at the top of this page, consisting of masses m1 and m2 and springs k1 and k2, with input force F on mass 1 and output displacement y2 of mass 2, the question that we would ask from a loading point of view would be, could we model this as a cascade system? That is, we'd model the system m1 and k1 with input F and output y1, and then model system m2 with input y1 and output y2. Could we make a block diagram as shown below, where we have a system h1 which takes in F and produces y1 for system mass 1, and a system h2 which takes in y1 and produces y2 for system mass 2. Can this be done? And the answer would be no, because of loading. The reason why is because the spring K2 also pushes back on mass M1, and this force is not represented in the model. We cannot treat the interconnection of these two mechanical subsystems as a cascade of them because of the issue of loading. We will study in great detail how to make mechanical models of systems like this in later presentations. At this point, I just want to identify the issue of loading to you, to have you keep it in mind. It's always important to consider when you're making interconnections of block diagrams.